At least a couple of students are here. So are we online? Tell me when we are online, yeah, then I stop. Okay, good.
Okay, so I think we can start. It's a real honor for me to introduce you today, Joachim Puls, from the Munich Observatory, in Munich University Observatory. He's been here many times since the early 90s, almost once per year, more or less. But this time is a different one. It's a different visit because of three reasons. The first one is that it's his longest visit. And this is thanks to the second thing that is funded by the Fundación Occident. And then the third one is that is the first time that we can be discussing all the time about science, because recently he has retired from his administrative and teaching duties at the university. So now he can enjoy just discussing with colleagues and friends about science. About his CV, the shortest version is that he's one of the most recognized researchers in the field of massive stars. But obviously, I can give you some more detail. He did his PhD in finished in 1987, and this was about radiation-driven winds. Afterwards, he's been concentrated mostly in the study of how massive stars, different aspects. So, for example, he has been very interested in the theory and modeling of radioactively driven stellar winds, and in this sense, he has been collaborating for many years with Stan Walkies. That is one of the other references in the field. He has been interested in numerical codes, especially he's the developer of one of the most used stellar atmosphere codes for massive stars, that is fast one. This was done in collaboration with his office mate Adi Poldra, that unfortunately passed away a few years ago. And he started this in collaboration with Artemio Herrero here at the IAC, with a co-supervisor of a student that is Quique Santolaya, that is also a reference for all the students from the massive star group at the IAC. And also he has been interested in many aspects of quantitative spectroscopic analysis of massive stars. And in this regard, he has been collaborating with many researchers in different institutions. He has almost 200 referee papers with researchers all around the globe. And he has written 2 annual reviews about winds and mass loss, one in ANA and the other one in APG. He has been president of what was initially the working group of massive stars and was the promoter, and it was thanks to him that this was transformed into IU commission, and was also president of this commission for a few years. He has several prizes from the German Astronomical Society, and he has a strong commitment with the massive star community during all this year, and especially with the early career researchers. And in this sense, for example, he has been the promoter of a very interesting initiative that will start next Thursday. That is the online lectures on massive star physics. But I think it's going to be great for learning many things about this topic. And then, yeah, last but not least, he has written a chapter in what is called Encyclopedia of Astrophysics, and this is about the stellar atmosphere. He did it in collaboration with Artemio Herrero and Carlos Allende, they are both here. So this is just a brief summary of his CV, and it's going to be great to listen to what you want to tell us one more. So whenever you want, Achim.
Oh, okay, gracias. Buen día, señores y señoras. Bienvenido a mi, whatever, a mi conferencia y gracias por venir. So these are my only Spanish words except dos cervezas, por favor. And I will no longer torture you with my Spanish, but switch immediately to English. So many thanks for this very nice introduction, which was hopefully a bit longer than my talk itself. Regarding the talk, I have a bit to apologize. Usually I'm timing my talks quite well, but today I started quite early at 4:30 in the morning local time to finalize on some James Webb proposal, which as usual, particularly since the observers always take so long, has to be finished only on the last day. So submission to date for James Webb applications is today midnight, something like this. So, good. So today I want to speak about stellar abundance determinations in hot massive stars, and the reason is because I'm working on this together here with my colleagues from the IAC, particularly Sergio and Artemio, but there are also, of course, other collaborators in this talk, particularly Sergio's students. I will come back to them in a second. Then my former PhD students, Jorge Rivero Gonzalez and Luis Carnero. And there is also, of course, Miguel Urbaneja from currently the University of Innsbruck, but he was also a former student here together with Artemio and also myself. And finally, I have to acknowledge the help of the VLT Flames Massive Star team, which was a big survey on massive stars. And particularly, I have also to acknowledge one of my former doctorants, John Sundquist, now professor at the KU Leuven. You see him here. Good. Yeah, so that was all. No. Finally, most important, I have to acknowledge a travel grant here from the Fundación Occident, which pays for my travel here. So thanks a lot to this foundation. But now let's start and let's set the stage, namely massive stars, where we are. We are in the upper part of the Hertzsprung-Russell diagram here in this regime. Luminosities 10 to the 5 to 10 to the 6. Temperatures for the hot, most massive objects around 50,000, down to, say, in the O-star regime, 30,000. Then we have the supergiants. And finally, we have also the A supergiants before reaching the red supergiant phase. And just to remind you, two stars which are visible, I have checked this around midnight also from here currently, are Betelgeuse and Rigel in Orion. Betelgeuse, a red supergiant, and Rigel, a blue supergiant. And when you look onto this constellation, you will really see the one shining red and the other shining blue. Good. So, see, massive stars have been called in a conference from the year 2007, cosmic engines. And cosmic engines is really the word which describes what massive stars are with respect to our universe. They are low in number, but they have an enormous energy output. 1 million solar luminosities. And this energy output is not only by means of radiation, but also by winds of different strengths. And as everybody should know, they are the progenitors of core collapse supernovae, of long duration gamma ray bursts, and of black holes. Massive stars are supposed to be the first stars, the very first generation of stars in our universe, and at least they are responsible in part for the cosmic reionization. We still do not know to which fraction, but approximately, say, 50–60%. They are more or less completely responsible for the first enrichment of the cosmos with metals. And they are important for galaxy people. So if somebody here is doing galaxies, they are important with respect to what the galaxy people call feedback. Namely, they enrich the environment, their environment with metals via red supernovae. Particularly important they are for the chemodynamical evolution of galaxies. And finally, last not least, they are very important for determining the energy and momentum budget of the surrounding interstellar medium. So, why do we speak here in this talk, or why do I speak here in this talk about abundances? Of course, we can model the evolution of massive stars. But if somebody will tell you the evolution of stars in general is a well understood topic, that's completely wrong for the massive stars. I will give you a couple of examples during the talks. And so at least we need to calibrate them and to test them. Why is it so? These are the evolutionary tracks with respect to the These are the tracks with respect to rotational speed as a function of effective temperature from two codes, and these tracks have been published and you find it on the net. So, and when you plot them for different initial masses, from 20 to 60 initial masses, you see that there is, at first glance, that there is a big difference into these two tracks. One, the above one is from the so-called GENE code, which is a Geneva working group on massive stars that has been calculated by Ekström. And the other one is from a code which is called STERN, actually a code which bases still on the, of course updated, but which bases still on the early work by Rudolf Kippenhahn. And it's very similar to the procedure in MESA, and both are starting their evolution at the 0-age main sequence with an initial rotational speed of 300 kilometers per second. But as you see here in the second code, there is only a small weak decline of the rotational speed until the end of the main sequence, and only then the speed is going down, whereas in the other code, the speed is more or less immediately going down for the most massive objects and only for the lower mass objects. It's similar to the other results. And since, for instance, rotation, as I will show you, is crucial for the mixing in stars, you can imagine, of course, that the predicted surface abundances of these modes are quite different. And therefore, this needs to be tested. Of course, maybe the truth is just in the middle, but we have to test this. First, for the specialists here, the main difference on these model grids is due to 2 points, namely at first, in the lower one, internal magnetic fields were assumed, adopted, whereas this is here more or less free of magnetic fields, but more important that different way, and there are currently some initiatives to unify this. So as you see, here we have a main sequence of the evolution of massive stars. It's unclear in many details, and therefore in later phases, so when we go to the giants, to the supergiants, red supergiants, and finally to the explosion, or to the potential. And therefore we have to test.
Joe, I think the microphone died.
My microphone is down now?
No, I think it's better if you use the hand one. It happened.
So sorry for this. I hope you can hear me now again. So And an ideal tool now for these tests is the measurement of CNO surface abundances. Why so? When we have a rotating star, particularly when it is rapidly rotating, then due to the so-called von Zeipel theorem, the pole becomes hotter than the equator, and there is a meridional circulation invoked, which finally can mix material from the core to the surface. In the sun, this is called Eddington-Sweet circulation, and generally now as well. But there are also other mixing processes, such as turbulence, or if we have here a rotational speed as a function of distance from the center, then there might be also shear mixing. So, and all these mixing processes then can bring material from the convective core to the surface. And this has been calculated, for instance, by Ines Brott in her work. And this is now the surface nitrogen enrichment for SMC, LMC, and galactic stars. And you see that at least for quite massive stars with initial masses of 40, already in the first million or years in their evolution, there is brought a lot of nitrogen to the surface. When the stars are not so heavy, so they are beginning here, for instance, with 15 solar masses, then this enrichment occurs only in the first 3 or 4 million years. And if there is no rotation at all, then nothing is happening through the complete main sequence, and only during the first red drop in this red supergiant phase, there is then this material brought to the surface. So these are predictions, and we might use them for calibrating our evolutionary models. However, even for single stars, and during this talk now, I will almost, not completely, almost speak only about single stars, though massive stars occur very frequently in binaries, but even in single stars, we have certain problems. And these problems are presented due to the winds and also because of strong, that was too fast again, also because of strong deviations from LTE, which is called NLTE. So the test by observational diagnostic becomes complex. What is NLTE? At first, I said we have these NLTE processes plus wind processes. So where do they occur? When we have non-supergiant stars, so BA stars close to the 0 H-man sequence, then we have to deal only with non-LTE, whereas for O stars and all other supergiants during the evolution, B and A supergiants and Wolf-Rayet stars, we have to account for both processes. So what is NLTE? NLTE is the negation of LTE. So this means non-LTE, or not non-local thermodynamic equilibrium. So it's simply a LTE and then everything which is different. What is LTE? This you should know from your courses. Namely, LTE is nothing else that when you know the temperature and the density of a certain stratification, you can immediately calculate the ionization and the excitation balance because of the Saha-Boltzmann equation. But this is only true when the collisions, when the number of collisions, oh no, everything breaks, when the number of collisions are dominating all other processes, in this case, the radiative processes. In those cases, when we have less and less collisions, because the density of the atmosphere becomes thinner and thinner, then at some point radiative processes will dominate, particularly for the luminosities and luminosities, which we are considering here. And then one has to do something different, and this is called non-LTE. So what you have to do is you have to calculate any kind of populating and depopulating rate of all electronic levels of all elements, ions, and so on, which are present in your atmosphere from the radiation field. Sorry, I'm such an idiot. where we are. Here. So from the radiation field, and this, of course, then also depends on the cross sections. And you have also to account for the weak, but nevertheless present impact of collisions. And this, as you can imagine, requires a huge amount of atomic data, both for these radiative and collisional cross sections. And it requires as well a very tricky iteration between the calculation of the occupation numbers and the radiation field. So both have to be converged in parallel. And when you have finally the occupation numbers, then you can calculate the emergent spectral energy distribution and the line profiles. Good. So you see, because of these non-LTE effects and also because of the presence of the winds, the tests become quite complex. There is another motivation for studying abundances, which I will not tackle today, namely, of course, massive stars. Because of their high luminosities, they live fast and they die young, and therefore they are an ideal tool to measure the metallicities of their current environment. And this is then independent of any kind of problem resulting from emission line diagnostics, as the people will know who are doing these things in nebula. On close scales, this can be done, for instance, for the most user-friendly, so to say, objects, the B dwarfs. This has been done by Norbert Pritschibiller in Innsbruck and co-workers, and he derived very interesting and nice results. And it can be also on extragalactic distances done for the supergiants, in this case for the BA supergiants, because these are the visually brightest objects on the sky. And it can be also done in red supergiants. Here's an example for a J-band line diagnostics, in blue the theory, and in white the observations. So you can imagine that one can get from this, for instance, the abundances of iron, titanium, and so on. Good, but we will not concentrate on this. We will concentrate on the CNO diagnostics to check our evolutionary models. Just to remind you, for the sun, the game is a bit different, and of course for other cooler stars as well. This is a famous table by Asplund et al. From 2009, where you see the abundances for the first elements in the periodic system of elements. And when you look on the abundances and their errors, in most cases, they are quite low. They are on the order of 0.05. And this is only possible, or has been only possible, after it became possible to calculate the atmospheres in 3 dimensions to account for convection. This is a famous work by Nordlund, Steinert, Asplund, and then a lot of other people who are able to do this. And when you include now these kinds of 3D atmospheres, then you can really find these kinds of very low uncertainties. Even more, since for cool stars you have many lines, and then the error of the mean is decreasing with the line number. Even more, since many people in this business forget to propagate the errors of the stellar parameters to the abundances, so they believe in their stellar parameters and do not propagate these errors. And even more, since at least at solar metallicity, the non-LTE effects, which are so complex, are not dramatic. For lower in metallicities, on the other hand, you also have to account for them, and then you might ask Carlos, then the game begins difficult again. Yeah, good. So to summarize and to finalize the first part of my talk, a reliable abundance determination requires at least 4 prerequisites. We need spectra with high signal to noise and high resolution. In the best case, we concentrate on slowly rotating objects, because otherwise the lines become too broad and too shallow. However, when we investigating slow rotation, then also this surface abundance enhancement would be to be expected low. So this is maybe not a good test. So in some cases, we have to account for fast rotating objects. And we need many lines from at least 2 ionization stages to check the reliability of the result. Namely, these different ions should provide us with identical abundances. Otherwise, something is rotten with our atmospheric model. Yeah, and for all this, we need reliable atmospheric model atmospheres, synthetic spectra, which are based on accurate atomic data, and that's a problem in its own. Yeah, I will give you a few examples to show what happens in the O-star realm. So this is a so-called O9.7 star. This is just at the beginning of the O-star spectral range, around 33,000 kilokelvin, surface gravity of 10,000. And in this case, I have indicated oxygen by green, carbon by blue, and nitrogen by red. You see, we have quite a large number of lines, not millions, but at least on the order of 10 or even 20 sometimes of these lines of two different ions, particularly in this regime here. In this regime here, where we have a couple of nitrogen and carbon-3 lines. And also in the realm of 5,000 to 6,000 angstrom, we have a couple of lines. So in this realm of the cool O-stars, we expect to have a similar accuracy as, for instance, for these B dwarfs, which I mentioned before. So on the order of 0.05 dex without error propagation. When we become a bit hotter, from 33 to 35 or 37,000 degrees, the situation decreases significantly. And for instance, the ionization stage 2, so single time ionized, vanishes. This is shown here. This is now an object at 36,000 Kelvin. Admittedly, it's a supergiant, so with quite a lower density. And what we're seeing in this spectrum is basically only hydrogen-helium lines and lines from nitrogen-3. No longer nitrogen-2, still no nitrogen-4. The nitrogen-3 here has some peculiar behavior. It has a slight emission. We will come back to this later on. And more or less no other elements except for carbon-3 here, these two weak features are visible in this wavelength range. Around 5,000, there are a couple of more lines, but that's it. Only very few lines. And when you become now even hotter, this is now an object at 53,000 Kelvin, so at the upper edge of our temperature scale, then we have more or less to live only with nitrogen lines. There are no lines from carbon and oxygen at all other optical wavelength ranges, and nitrogen-4 now goes into emission, and there are 2 lines from nitrogen-5, but that's it. So you see, for the hot stars, we have, at least in the optical and similar in the infrared, only a very limited number of lines, mostly from nitrogen and nothing from the rest. But of course, the optical and the infrared is not everything, so we have also the ultraviolet. Let's have a look. This is the ultraviolet spectrum of a star at 40,000 Kelvin temperature, supergiant with a strong wind. One of our favorite stars in our business, called Zeta Puppis, on the southern sky. And this includes now a rarely observed frequency range down to 900 angstrom, which is usually not observed, only with very special telescopes, as here with EUVE. Good. And when we look on this spectra, they look a bit different from the optical ones. Namely, we have these broad lines here, which are called P Cygni lines, and these lines are formed in the wind, because also in the wind, at least for the ground state transitions, these are resonance lines, so ground state transitions, the optical depth remains strong, large, until the end of the wind, so to say. So let's look what we have here. At first, we have a couple of photospheric iron lines. All these here is not noise. These are photospheric iron lines, typically from iron 4, 5, and 6. So they might be very interesting, because in the optical we have only one iron line. So that's not much. But when we want to get the abundance of the iron, then we have to concentrate on the UV. Then we have few carbon lines, few nitrogen lines, and one oxygen 6 wind line, very high ion, very interesting line here, and two photospheric lines from oxygen 4 and 5, which we need for the hottest stars, because in this case we have no optical photospheric lines. So as you see, that's not very much in the ultraviolet as well, except for iron. And when we now make a comparison between wind and photospheric lines, then we find a couple of pros and cons. Namely, at first, the range. Wind lines, as I just showed you, are mostly located in the ultraviolet and extreme ultraviolet, which is expensive and limited. In future, we might have only one, if at all, satellite instruments, a habitable world observatory for this. Currently, we still rely on the HST and this Ulysses mission. In the photospheric lines, we have the optical ones, which I just showed you. Which I just showed you. And in the ultraviolet, we have these few photospheric lines from oxygen, which might be inevitable, and a multitude of iron lines. The number of lines and the number of ions is limited for the wind lines. For the cool O stars, it's okay. For the hot O stars, it's no longer okay. And the influence of rotation is large in the optical, simply because the lines become so broad due to rotation and then weaker. So there is overlap with lines, whereas because of the large width of these Picigny lines, rotation does not play a big role for the wind lines. It plays a certain role, but not much. Yeah, and then we come to the real cons, which would speak in favor of optical spectroscopy. Namely, the wind lines are not only broad and affected by the wind, but they are even affected by so-called wind inhomogeneities. And this is shown in the next slide. Namely, the reason that these lines are so broad has to do with the Doppler effect. Simply because the velocity becomes larger and larger in a wind, it's more or less monotonically accelerating. We have to account for the Doppler shift. And in each region of the wind, the lines are illuminated by fresh photospheric light. This is shown here. This is the velocity field proportional to the velocity, to the frequency. And here we say at each point we have an illumination by fresh photospheric light. But now when we make a perturbation in the velocity, a certain part of this velocity field is shifted to higher velocities and thus higher frequencies, and we get some additional irradiation. That's the important point. And because of this additional irradiation, our line acceleration becomes larger. When the line acceleration is larger, then the velocity goes up. So this is a circle. And finally, we have a very large velocity perturbation from an initially small one. So simplified, the perturbation and the radiative acceleration is proportional to delta V. Yeah, what is the result of this kind of perturbations? This is shown on the next slide. If we calculate now a hydrodynamical model accounting for these kinds of instabilities, we see it looks a bit different than a standard wind, which would be denoted by these dashed lines, namely that we have here some spikes in the velocity field, which are currently braked. The braking is when two shells are colliding, then we have a shock, and there is a braking inside the shock. And we have here also high density and low density matter, though the spatial time average structure is not too different from the stationary ones. But such an inhomogeneous structure seriously affects the radiative transfer, and hence all derived mass loss rates, ionization fraction, and wind abundances, which we would infer from observations if we would use a smooth wind model. So we have in some way to account for these disturbances for these kinds of density and velocity field distributions. And this, at least at the moment, can be done only in a very approximate way, if at all. So there is a real problem. Since we do not know the real structure of these inhomogeneities, we do not know the exact wind structure, and therefore we cannot account or correctly derive finally the abundances. Yeah, just to show you that we can do this also in 2D, this is a recent simulation by my former student John Sundquist, now as I said, head of the KU Leuven, one of the groups in KU Leuven. And he has calculated at least two-dimensional models accounting for these kinds of instabilities. And as you are seeing, when you are starting with a smooth distribution at some point in the hydrodynamic simulation, you will you will find large inhomogeneities. The 1D shells from before break up into statistically isotropic small scale slopes, clumps, and so on. So this is something what would happen in such an unstable wind in more than one dimension. So that's the first problem. This kind of instability affects the analysis of wind lines. But even more, since we have now these kinds of not only non-linear, but only linear, but non-linear instabilities, so these disturbances collide and they form shocks, and the shocks are braked. This is shown here in this kind of simplified movie. Therefore, we have also these shocks, and shocks means high temperatures, which are proportional to the square of the velocity jump. And therefore, the temperatures are quite high, on the order of 1 million Kelvin or something like this. And you can imagine that a radiation field, even if the filling factor is not large, but has such high temperatures, this might have an impact on the ionization. At first, these predicted X-rays are not only predicted, but also observed, both with Einstein, Rosa, Chandra, XMM, Newton. They have a temperature, a shock temperature of a couple of million Kelvin, and an X-ray luminosity of 10 to minus 7 bolometric luminosity. And the idea is, as a pitahaya here, we have more or less a almost smooth wind, and we have a large number of these colliding clumps, which then create this kind of X-ray field. And this X-ray field is now particularly in the extreme ultraviolet, also strong. That's a long frequency, long wavelength tail of the radiation X-ray. When you assume for the Rayleigh-Jeans regime in X-ray, then you are in the EUV. And you see here, this X-ray emission, the EUV tail of the X-ray emission is much stronger than without it. And since a couple of important ionization stages are located just on just around 229 angstrom, you can imagine that the wind ionization of important ions is affected by this kind of X-ray radiation. So, to recapitulate, photospheric features are not only weakly affected by inhomogeneities, namely the photospheres are thought to be unclumped. However, there are recent calculations and simulations which also show us that maybe also this is not true. It might be that even the photospheres are inhomogeneous, and then we have to restart our analysis again. And these photospheric features are not affected by X-rays, since the emission starts roughly only in the outer wind. Good, so now let's see. We have 10 minutes, I guess. Yeah, no, 15 minutes. All right, so the last point in this case, which speaks in favor of photospheric lines, is the complexity of the transition. What do I mean with this? In the ultraviolet, the transition is from the ground state to the first or second excited state. And so this can be described quite easily, whereas optical lines connect high-lying levels, and there something can happen. An example is showing in the next slide. You might remember from the observational slides that there were in the intermediate hot O-star domain around, say, 35 to 40,000 degrees. We had this kind of emission here, of line emission at 4,600 angstrom. And this emission actually has a spectroscopic designation. It's called the F features, and it's observed in a large number of stars, not only supergiants, but also dwarfs with thin winds. So there is no direct relation with the winds. So just to show you here, I have a simplified Grotrian diagram, very simplified, for nitrogen 3. And this is here the transition between 3D and 3P. And to get such an emission, when you know about radiative transfer and so on, then you find immediately the conclusion that the ratio of the occupation numbers of the upper level to the lower level of this transition must be much larger than the LTE ratio. When it would be at the LTE ratio, you would have absorption, but when it's larger, you get this kind of emission. So how to get this upper level more populated than the lower level? This is the question. There were a couple of ideas in a long-standing debate, but finally my doctorand Rivero Gonzalez found out the real reason for this. Namely, it is the pumping of the upper level by this resonance line here. So there is a resonance line, and this resonance line is strong, and it can bring electrons to this 3D state in such a number that the 3D state is overpopulated compared to the 3P one, and then you get this kind of emission. And please note, this resonance line is now in the extreme EUV at 1374 angstrom, something which we can almost not observe. So all this is pure theory. So this I will not explain here. The important point just to remember is that this emission is strongly depends on the EUV. And this is not only true for this line, but for a large number of other lines, for instance, this famous carbon-3 4650 lines. So when we have a look into this EUVE range, then we have here the radiation field. Now look, this is only 10 angstrom wide here. And this is at an optical depth of 0.3, so roughly in the formation region of these lines. And you see there's a lot of things are going on in this 10 angstrom. And our line, our nitrogen 3 line, the resonance line of nitrogen 3 is located here. So just to show you it in the zoom, we have the nitrogen 3 resonance line. Actually, these are 3 components, and there are some lines from other elements. And this is one of the major problems. Namely, there might be a coincidental line overlap. And in this case, there would be such a line overlap between one of these nitrogen 3 resonance lines and an oxygen 3 resonance line. Of course, this depends, for instance, on the correct wavelengths of this oxygen 3 resonance line. Now, this is a well-known element, so here the wavelengths is quite well known. But of course, there are other lines, particularly iron lines. And for these iron lines, the wavelengths are not so much known. And see here, there is, for instance, one of these iron 5 lines. So coincidental line overlap might have an effect whenever we have pumping by resonance lines. And so these overlap effects depend on the accuracy of these all these background lines here. Then, of course, we have to know the abundances, not only of the element which we are analyzing, but also of those which are overlapping here. And finally, we have to know the line broadening, particularly the so-called microturbulence. So let's make a test. Without any line overlap in the EUV, there would be no such emission lines, at least at cooler temperatures. They still would be in absorption. When we include all the line overlaps, then we get this one. So you see, that's quite a difference with and without such line overlaps. Good. So in the original publication by Rivero Gonzalez, it was argued that the line overlap is only due to oxygen. So a simple trick is reduce the abundance of oxygen, then it should go into absorption. So when you do this, you see, you would see nothing. So I've reanalyzed then the problem, and indeed it is the iron 5 line, which then still keeps it up. And only when we reduce also the impact of the iron line, then we get this, what is shown here in green, namely at least in absorption. There's still some impact. So you see, all these line overlaps have a big impact on the analysis of certain lines, and this is what I meant with complicated, complex line transitions. Overlap in the extreme ultraviolet, which we have a handle for only theoretically. Good. So now the last 5 minutes. Yeah, I think I'm in good shape. The last 5 minutes, I will show you a couple of, this is now not interesting, a couple of results. Before I'm showing the results, I will remind you about the CNO cycle just mentioned before. Namely, the CNO cycle is actually a B cycle, the so-called CN cycle, and the ON cycle, and the ON cycle sets in later than the other one. So when you look on the evolution of the carbon, nitrogen, and oxygen abundances, then you see that in the beginning of the CNO cycle, at first oxygen remains more or less constant, and carbon is burned into nitrogen. So nitrogen increases, carbon decreases, and then carbon remains constant later on, and the second cycle sets in. And in this case, then oxygen is burned into nitrogen. So these are two cycles which have different time scales. One which is quite fast, the CN cycle, and another one which is quite slow and sets in later, the ON cycle. This we need for our next slide. Namely now it's not working. Namely now, one can show that the ratios N over C versus N over O can be solved in two limited cases analytically. Of course, they depend on initial conditions, but nothing else. That's a good thing. So for instance, in the early CNO cycle, as I told you, oxygen remains constant and C is converted into N, whereas when we have now CN equilibrium, C remains constant and oxygen is converted into N, and this is this limiting line. And if we now do some kind of abundance analysis, then indeed, in this case for a sample of 74 galactic O stars, in this case we find that the stars behave as they should. All stars are more or less just within these limiting cases. And indeed, you see one of our major problems, namely because of the few number of lines and all these other things which I explained to you earlier, the errors are not 0.05, but on the order of 0.2, sometimes even 0.3. This was done by our colleague Fabrice Martins, and the same has been repeated by my student Luis Carnero for 18 slowly rotating objects, and we find more or less the same, even here with somewhat larger error bars. I think we have a bit more accounted for the error propagation. Anyhow, the result from this would be that the derived surface abundances are reasonable, though the uncertainties are large, and particularly that the derived surface abundances are consistent with CNO cycle products. One has to say, though, that we have in both samples here quite highly enriched objects, highly enriched at the surface objects, which are dwarf stars. And this has a certain problem. Namely, on this side, this sample here, these are slowly rotating stars. So when they are significantly enriched, as for instance for these two objects, they must have been rotated, they must have been more rapidly rotating earlier, at least if we believe in rotational mixing. This is, of course, unproblematic if these stars were supergiants, because the supergiants have a strong wind and this leads to breaking. However, for enriched dwarfs, this becomes very problematic unless there's a very rapid deceleration of these dwarfs. I will come back to this in the last slide. So this was CNO. Now what about nitrogen versus helium? These are, again, two different analyses, and the result is more or less the same. At first, nitrogen increases where helium more or less remains constant, and at a certain point in the evolution, then both things are becoming enriched at the surface of the star. So at that time, there was the conclusion by this guy Grin, namely, though the mechanism that brings nitrogen and helium to the surface may still be unidentified, so is it rotational mixing or not, it is one that brings a mixture of gases to the surface that has a helium over N abundance ratio that is expected from the CNO process. So this was true until half a year ago or something like this. Namely, this is now connected and related to my work here. That's the same plot as before with a different scale. And this is now some new findings which were obtained by Carlos Martinez Sebastian. And he wrote a paper on this, a letter on this, which has been submitted just today. So we can celebrate him. And the reason is there is a slight difference. Namely, we have used now not only the LMC, we have used the Milky Way, and we have increased the sample to a much higher value. It's a sample now of 190 stars from the so-called Jacob survey by Sergio Simon Diaz. And what we are seeing now is that we find also hydrogen and helium with quite a peculiar ratio in this regime here. Indeed, when we look carefully, this would be the star in the older work, which is now here a total sample of stars. Roughly 20% of the sample have high helium and low nitrogen. And this is just the other way around what one would expect from rotational mixing in single stars. Namely, in single stars, you would expect that at first you enrich nitrogen and then finally you enrich hydrogen, helium. And that would lead to something like this here. But this here is the opposite. High helium, low nitrogen. And we have checked all evolutionary scenarios. This is, you can believe me, more or less impossible with standard single star evolution. And so what is the conclusion? It's not single stars evolution, but binary evolution. And what we are seeing here are the products from a past binary interaction, in this case, mass transfer between two objects. And such a mass transfer can, as shown by Jin et al., often lead to strong helium, but only moderate nitrogen enrichment of the mass gainer, as we see it here. And as I said already before, we have indeed a large number of binaries in our O stars. So that's the explanation of these strange objects. And Sergio, Carlos, and colleagues have suggested that we will investigate these stars, particularly when investigating no longer the single star scenario, but the binary scenario. So let's see what the referee is saying. And that was it for today from my talk. Just let's come to the conclusions. Yeah, I leave you with the conclusions, and I'm open to any kind of questions. And I think I was 2 minutes too long. So sorry for delaying your lunch. Thank you.
Thanks very much. It's very nice talk. I was wondering, you had a note there about the Doppler shift of the resonance lines and how that fits back on the bandas that you measure in the optical one. Do you get the exact shape for the lines depending on the right, if you get the wrong Doppler shift? And is that Doppler shift predicted by the models correctly, or you have to tune that with some parameters?
You have to.
So yeah, so we can reproduce the shapes of these Pisunian profiles quite well. The problem, of course, is that you get different strengths in dependence of abundance. So we might find a fitting profile, but in this case, and in most cases, the specific transition within a thermal width, not within the total width, but in the thermal width, is saturated, and so we cannot learn so much. So it could be also the velocity field could be different, for instance, due to these inhomogeneities, and we would more or less get still the same shape out. That's the problem. So when we could obtain from the shape of the profile the shape of the velocity field, then everything would be fine. But since we have so many wiggles, so to say, so many clumps going up and down, this is statistically canceling out. So we can reproduce the observations for the wrong reasons, for instance. And this is a problem of the abundances.
Thanks for the very nice talk. You mentioned in passing the production of X-rays due to shocks of clamps in the wind. And you mentioned that there is observational evidence for that. I was wondering what kind of observational evidence? You mean that there is X-ray light curves with flaring and this kind of stuff? And what is the time?
So that's a very interesting question. So the question was, what do we know from the observations on the X-rays? So at first we can really observe the X-rays both in the soft as well as in the hard band. So say from 200 EV on to 10K EV, something like this. And therefore we see then the X-ray emission, which is quite strong due to the high temperatures, say typically 10 million Kelvin. And of course we have checked for the variability. The variability is quite low. And when you bring this into a statistical argument, how many of these shocks you need to produce such a low variability, then you can find a number on the order of 50 to 60,000 of these shocks. This is in a paper by Yael Nazeh et al. So that's the first thing. And the other thing, of course, is that we see a lot of X-ray lines from helium-like, mostly helium-like elements. So in this case, of course, high ionization stages and all this, the ionization degree and so on, is very consistent to what we are predicting.
I see a hand in Zoom. I think you can unmute yourself and ask the question. Hello, WRH, the person in Zoom with the hand up. You can unmute yourself and ask a question. Or not. Any other question in the room in the meantime? Do you hear us in Zoom? There is someone with a hand up. Do you want to ask your question?
While we're waiting, may I ask a question to Joe?
Sure, please.
You mentioned microturbulence in passing, that you need to know the microturbulence to derive good abundances. But how do you know it from your spectral analysis here?
This is a very good question. It's a question, of course, on the topic you and your colleagues are working about. So what we know is, of course, only one more or less direct and another indirect argument. The direct argument is that we can look, or in principle at least look, into the cores of stars which are extremely low rotational speed. And when you measure their widths, then you will find that it cannot be larger than, say, 20 kilometers or so, maybe 10 kilometers, but that's it. So this is a direct point, but of course you need to have stars with a very, very low rotational rate, and there are only very few stars which have such conditions. The indirect argument is the question, what kind of microturbulence do you need to obtain a certain equivalent width? And this is particularly regarding the question of abundances, because you want finally to have that a large number of lines are reproduced by such an equivalence, meaning by such a microturbulence, that you get from all lines the same abundance. So it's an indirect argument. And when you play this game, so what kind of microturbulence you need to get the same abundance for all kinds of lines, then again, you find, for instance, for the supergiant stars, values on the order of 20 kilometers per second maximum as a maximum, whereas for the dwarfish stars, when they become cooler, this value goes down and down. And I think the lowest value we have measured in quotation marks is on the order of very few kilometers per second. But all this is more or less indirect, unless you believe the measurements from stars with very low rotational speeds.
Yeah, agreed. Are there such stars in the early O-star domain, or is that more in the late? The very slow rotators. Do you know that? I am unfamiliar, actually. Yeah.
I didn't get the second part of your question. I understood it until the earlier.
Yeah, the slow rotators.
Yeah.
Are there slow rotators, say, in the early O-star luminous regimes?
Yeah. This is a very good question, and we are asking ourselves the same question, because, as you know, we might have also a couple of these stars which are magnetic and are break down to magnetic fields, as is the case for this famous star Tau Scorpii. And then you can always argue, because they are magnetic, they are outliers.
Right.
So this is, I do not know, maybe Danny, do you know any proven non-magnetic stars, dwarfs, which have a low rotational speed? What? Okay.
Okay, thanks.
Yeah. So but we need really something which has a rotational speed below 10, because yeah. Okay. For A stars, yes. Yeah. Okay. So Danny, if you have not heard, was saying that there are quite a lot, but the constraints on the magnetic fields are not so strong.
Okay. Yeah, but that's okay. That's a good sign that there are a few.
Yeah, certainly we will have a look into our database and check this, because this is one of the points and topics which I'm doing here together with Sergio and his students.
Yeah. Great. Thanks.
That's Wolfram Harman, I guess, yeah, but you should ask. Wolf Rainer, if it's you, then please ask your question. I think there's lunchtime also in Germany. Okay. So. Here. I am not allowed. Let's see. Allowed to unmute, yeah. Yeah, he could have written his question when he writes a comment. Yeah. Okay. So then let's stop, and I wish you a good appetite.